All right, and we are back. And so the next part that we're going to look at is these ACDC circuits in response to certain frequencies. So just like what we've been doing before, anytime we add in a capacitor or an inductor or things like that, it now has the ability to filter out certain frequencies, and we can see that with exactly these frequent or these circuits. Sorry, these circuits just as well. And so the big thing is when we look at them, we have two capacitors in the circuit. So we have at our, if we take a look at the outputs of these guys, one of the capacitors is going to drive the low end of our frequency spectrum, and the other one's going to drive the high end. And then when we combine these two together, this is going to give us our curve, our bode plot, and we're going to be able to kind of see and plot out what should my voltages be for this range. Do I see any attenuation? So basically what these guys are going to act like is they're going to act like band pass frequencies. So they're going to allow everything in between the two frequencies that we calculate, and I'll show you guys how to do that and what we're doing with those. And then we'll go through an example with that. But basically what it is, you're going to see that, any time when we get to the middle, in between these two frequencies, we're going to be pretty much at max voltage that we could get out of here. And we're going to be shifting them up and down based on the DC portion, things like that. But we're still going to see the typical curve. So we're going to see at low frequencies, it's going to be attenuated down. We're not going to see very much output. Then it'll get up to, we'll pass our critical frequency. It'll climb to the high point, and then we'll see it stay there. And then when we get to the second critical frequency, it's going to drop off. So just like what we've been doing before, now we're looking at, now we've created a band pass filter, essentially with using two capacitors instead of a capacitor and inductor. So like I said, these are just different ways to look at it, and based on all these guys, the idea here is what is my circuit doing? How can I calculate it? And so really, we break it down into pieces by small pieces. First we did our AC portion, then we did our DC portion. Now we're going to be doing these calculations based on what is our frequency doing. So the nice thing is the DC portion, we only have to do that once because frequency doesn't affect DC. It's one frequency. There is no frequency. It's always on. And so when we go through that, we'll only have to do the DC portion once, but we're going to be doing our V outs for each of our frequencies. So our critical frequency on the low end, the high end, and then one in the middle. And then our F middle calculation, that's going to basically be where our value is the highest in these circuits. So that that'll be the highest point. So other than that, right around it'll probably start dropping off a couple of millivolts here and there, and then this will be the pinnacle of it. So that's kind of the idea why we're calculating that. So let's go ahead and get started with this guy, and we'll start off with our regular circuit with what we've been doing so far. Now again, remember, this isn't the only style of circuits there are where we want to combine AC and DC together. This one just kind of covers and handles pretty much everything that we want to go through it, so that's why we use it. So we got R1, R2, R3, capacitor 1, capacitor 2, R-gen, and V-gen. Okay, so one of the things we want, and of course cross T2 as our V out. So one of the things that we want to look at is when we're looking at these critical frequencies, here's kind of some rules of thumb. So when we're doing this, we're going to find FC1 and FC2 based on this circuit. And these are going to come from capacitor 1 and capacitor 2. So what we have here is just kind of a couple of ideas and rules that we've learned before, but just kind of to see them in an actual application. So at our critical frequency 1, our X of C for capacitor 1 is, and I put this in quotes, normal. It's not obscenely high, it's not obscenely small, it's where it should be. It should be close to these values. It should be what the resistance values added up. So at a critical frequency 1, the reactance of capacitor 1 is quote unquote normal at this frequency. Our XC2, however, so the reactance of capacitor 2 is huge. So think 500 kiloohms. When we're looking at things, 3,000 ohms, 4,000 ohms, even 10,000 ohms, we're looking at these things. The capacitor 2 is going to be huge. We're looking, like I said, 500, 600, 700 kiloohms. values a lot larger. So this is kind of where we get into the assumptions that we make. If things are 10 times larger, 10 times smaller, we can effectively ignore them, treating them as an open and a short, respectively. So that's kind of the one rule of thumb, is at their XC1, so at a low frequency, this capacitor 1 is going to be kind of a normal value. XC2 is going to be huge and going to be gigantic. So then when we move to our FC2, and just real quick, remembering that this is what it's going to look like. So here's our FC1, here's our FC2. This is our frequency range. We're starting at 0. This is our amplitude, how high up we're going. And then somewhere in this middle spot here, this is going to be our F mid, which we'll calculate here a little bit. But anyway, so that's the idea of what we're doing. So as we increase our frequency, we're going to see these values. So at our FC2, so critical frequency 2, the reactance for our capacitor 1 is almost 0. Okay? Because we remember, as the higher frequency you get, the lower the reactance value of that capacitor is going to get. So as we keep getting higher and higher, the thing's going to get smaller and smaller until it's pretty much 0. So it's a short, non-existent. And then the reactance for capacitor 2 is quote-unquote normal, because it's the value of the resistance that it sees for the rest of the circuit. So how do we calculate these points? Okay, so what we need to do is, to find these values, is we need to take the R Thevenin at each of the capacitors and solve for the frequency. Okay, the larger the capacitors is going to dictate the smaller end of the frequency. The higher value of the capacitor is going to, I got that backwards. The higher the value of the capacitance, the lower the frequency that it's going to be. The lower the capacitive value, the higher the frequency is going to be. So that's kind of the way to distinguish between which one we need to use for the high end or for the low end. So in this case, C1 is our larger value in capacitance, C2 is our less one, generally. Not always the case, but generally that's going to be what's going to happen. So basically with this, so at each capacitor, we're going to solve for the frequency. So we come back and we look, what is our R Thevenin at capacitor 1? So we're going to solve for the low end first. So we come back and look. We're going to short out the supplies when we're dealing with Thevenin, remember. We remove the load, short the supplies, solve for the resistance value. So in this case, we have capacitor 1 is going to sit right here. So we got point A, point B. This is now connected to ground. This is where our generator was, but we've shorted them out. So we take out our RGen and our VGen. Then we're going to have this guy come across. It's connected to R1. And I'm just referencing this drawing again. So then R1 is connected to R2 and R3. And those guys go in parallel, because remember, off of R2, this was our DC power supply, but it's shorted to ground. So it's, we can say that this is shorted to ground right here. And then the last piece we have is our capacitor 3, or I'm sorry, our capacitor 2. But remember, at a really low frequency, this value is huge. It's going to be 10, 15, 20 times larger than R2 or R3. So we can effectively consider that an open. So if that's an open, we don't even have to draw it in at that point. So over here, this is C2. This is an open. Our generator was a short. Our VDC is a short. Okay, so now we need to solve for the Thevenin voltage across this entire circuit. And so in this case, our R Thevenin is going to be equal to R1 plus R2 in parallel with R3. So that is the value, because remember, at our critical frequencies, our reactance of our capacitor is equal to the resistance. And this is the value we're looking for, the resistance. That's all the resistance it sees. So then when we calculate it, we have our FC1 is equal to 1 over 2 pi times our R Thevenin at C1 times the capacitance of C1. So then we can plug those values in and get that frequency. Once we have that frequency, we can run through the set of calculations specifically for the homework to solve for what these values are going to be. Now, one of the things to remember is these are going to follow the exact same uh, patterns that we had when we were talking about regular critical frequencies. So the phase angle, remember what the phase angle is going to be at a critical frequency. Same thing is going to happen to here. It's also going to be the -3 dB power point, half power point, all that kind of stuff. 0.707 of the max voltage coming out, things like that. So remember all those tips and those tricks that we've already learned, they still apply to all of this. Okay, so that's how we find the R Thevenin for capacitor 1. So now we need to come back. Now we need to solve for R Thevenin for capacitor 2. And that's really all the farther we're going to do. We're not going to put the load back in. We just want those frequencies. Then we'll go back through and solve it with those frequencies. So remember when we did Thevenin, we did all the different steps. Right now, all we're interested in is just what is this R Thevenin. We don't care about V Thevenin. We don't care about the redraw. We just want to know what resistance is this capacitor seeing. So when we come back to R Thevenin at capacitor 2, so over here, here's capacitor 2. So we're going to go back through and redraw it. So if we look, capacitor 2 on one side is connected to R3 and R2 in parallel, but it's also connected to the R1 going to ground because the supply is going to be shorted out. Capacitor 1, remember when we're solving it at our high frequency, this value is essentially a short. So take that into consideration so that way it includes R1 and going to ground. So we end up with, this is the circuit that we have when we solve for our R Thevenin at capacitor 2. So we're going to start over here. We've got A and B. This part's going to ground. This was C2 that we took out. So he comes in. We know for sure that it's in parallel with R3. R2 comes down and around because it's also connected. So VDC is a short. So that's connected to there. Then we come into here, and then we come down. So this is our generator. From here to here, this is C1, because like I said, at high frequencies, it becomes 0 ohms, so it's essentially a short. And so now our R Thevenin at capacitor 2 is equal to R3 in parallel with R2 in parallel with R1. So now we can go through and we can solve for those values, and again, FC2 is going to be equal to 1 over 2 pi times our R Thevenin for capacitor 2 times the capacitance of 2. That's going to give us our 2 points, and now we have our 2 critical frequencies. Then the next step that we have to do is we have one last frequency to solve for it, because this is going to give us our max voltage out. So we call this one our F middle. So F middle, it's very easy to calculate. You take your frequency, your critical frequency 1, you multiply it by your critical frequency 2, and you take the square root. And again, the reasoning behind this gets into some of the deeper calculus, and honestly right now I don't need to go into that. So we're going to kind of, accept that that's where it is, but that's how we find our F middle. So we take critical frequency 1 multiplied by our critical frequency 2, take the square root of that value, and then we're good. So then, at that point, now we have our new 3 frequencies to solve for. Then we're going to go through and solve for the voltage out at each of these points. So now the next thing I'm going to do is I'm going to run through a practice problem for you guys on how to solve everything with our frequency response added in. We're going to go through, we're going to solve for the angles, because again, those are critical to what we solve for, or what we want to see when we solve for these guys. Make sure we did them right. So we'll go ahead and slide it up here. We'll start off by drawing this is kind of our standard circuit. We can add things, we can take things away from this as we want, but this is just kind of our base for these types of problems. So we have our V out here. We got this. So we have our R1, R2, R3, capacitor 1, capacitor 2, R-gen, and V-gen. Okay? So now, like I said, so before with the problems we had, we were given a frequency to work with. Now we need to solve for these frequencies. So the first thing, or the list of things that we want to solve for is we want to solve for our V out DC, and that's not going to change. We want to solve for our critical frequency 1. Then we want to solve for our V out max at frequency 1. We want to solve for the V out minimum at frequency 1. And we want to solve the V out AC in peak to peak of our critical frequency 1 and its associated angle. So like I said, there's a lot of little letters that we're using to designate things, and I do apologize for the use of those, but really all I'm using it as a designator. A lot of times when I write lowercase, they're just subscripts, and all they are is they just helping us clue in on what we're looking for. So remember, so like with this one, V out, MX is max at frequency 1. It's just a shorthand way of writing what exactly am I looking for. If you want to call them something different and label them, that is just fine. All I'm doing is I'm just labeling these guys just so I can keep everything straight. So then, after we solve for this value, we want to solve our critical frequency 2. We want to find out the V out max at our critical frequency 2, the V out minimum at frequency 2, the V out AC, which is in peak to peak at frequency 2, and its angle. And then the last thing we want to do is solve for our F mid, and then the V out max, F mid, the V out minimum at frequency mid, and the V out peak to peak at frequency mid with its angle. Okay, so the values that we have is, let's plug them in there and then let's get to solving it. So we have capacitor 1 is 77.08 nanofarads. Resistor 1 is 1.2 kiloohms. Resistor 2 is 5.1 kiloohms. Resistor 3 is 1.3 kiloohms. And capacitor 2 is 470 picofarads. Our VDC is a positive 16 volts. Good heavens, I can't draw. Plus 16 volts. Our RGen is 50 ohms. And our VGen is 5 volts peak to peak. All right, so now that we have those, so let's just go ahead and get in started. Let's take care of the easy one right off the bat, which is our DC redraw. So when we look at this circuit, we're going to see what's all connected to our DC voltage supply. So R2 is definitely connected, and then when we hit this node that everything else is connected to, we look in all the directions. R1 we're connected to that, but then we go to C1. Capacitor 1 is going to act as an open to DC, so that branch is going to be open, so R1 is going to be connected but hanging out with nowhere else, so we can ignore R1 because no current is going to flow down that path. C2 is going to be an open, so there's going to be no current flow that direction. So the only place that we have our DC current, VDC, is simply our DC supply, R2, and R3, with this being our V out across R3. So when we have just two resistors, it's simply it's a simplistic circuit. It's just a series R resistive circuit. We can use voltage divider. There's no phase angles, nothing else. So when we do that, we're going to have, so V out DC is going to be equal to the voltage drop across R3, which we can find by taking R3 over R2 plus R3, multiply that by our VDC. So that comes out to be 1.3K divided by 1.3K plus 5.1K. Multiply that by 16, and that gives us 3.25 volts of DC bias. So there's our V out DC. Like I said, we solved the easy one first. One done. Okay, now for the next 12 that we're going to solve for. So I'm going to switch colors. And so now what we need to do is we need to solve for our critical frequency 1. So the first thing we need to do is we need to find the R Thevenin of capacitor 1, because that's going to dictate it, because it's the larger of the two, and it's in this position over here. So when we look at this guy, we're going to draw in what the capacitor is seeing. We're removing the capacitor and looking at what is there. And we short the supplies. So we have our Rgen is shorted, and then the other side of capacitor 1 is connected to R1, which is also connected to R3 to ground. So we're just following this loop over and down. And then R2, since our VDC, which is another power supply, is shorted, this point goes to ground. So we can just bring that down like so. We have R2, we have our capacitor, which remember at our low frequency is going to be an open. So this guy we're not even going to take into consideration because it's just an open. And so we're left with this. So our R Thevenin at capacitor 1 is going to be equal to R1 plus R3 in parallel with R2. So those values come out to be 1.2K plus 1.3K in parallel with 5.1K. So this is going to be 986, and this is 1.2K. We add those together. So our R Thevenin at capacitor 1 is equal to 2,236 ohms. Okay, so now that we have that, we can solve for our critical frequency. So FC1 is equal to 1 over 2 pi times this resistance value, because the capacitor has to be equal to that at critical frequency, 2236. And then we multiply that by the capacitor, which is 77.08 nanofarads. And when we get through with that, the critical frequency we come up with is 903.238 hertz. So now that we have that value, now we can go through and let's solve for what our voltage out is going to be at this frequency. So we come back. So this is going to be our AC redraw at critical frequency 1. So we have our Rgen and our generator going to ground. We have capacitor 1, R1, and then that's connected to R3 to ground. And then this is connected to R2 and our capacitor. So we're just doing just the AC portion. We're ignoring the DC generator. It's shorted to ground. Remember our superposition. We're looking at one generator at a time. Okay. So now what we need to do is we need to find our X of C1 and our X of C2. And I'm going to kind of do this, and I'm going to prove to you guys, that we're looking at this guy, that we can safely ignore our capacitor 2. So capacitor 1, when we solve for the reactance, is 1 over 2 pi times the frequency times the capacitance. And that value comes out to be 2286 ohms, which it should, because that's what we calculated up there. And the next value we have for the reactance for X of C2 is 374.9 kiloohms. So if we look, R2 is 5.1K, R3 is 1.3K, R1 is 1.2K. This thing, the 374.9 kiloohms, is way more than 10 times any of those values it's in parallel with. So we can effectively remove X of C2 and the capacitor 2 from this equation, because it's considered an open, because it's so huge it's going to have zero effect, or not zero effect, a very, 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 very minute effect on this total resistance. It's going to be, within a few ohms of what this value is if we were just to take it, so we can effectively ignore it. Okay, so with that, kind of proven that we can ignore that value, our impedance total is going to be equal to our Z series, which is going to be the RGen, capacitor 1, and R1. And honestly, RGen we can leave out because it's 50 ohms, and it's going to be way less than 10 times less than either one of our XC1 or R1. So we can kind of throw that guy out. So Z series plus our Z parallel total. And so this group right here, this is the impedance of our parallel total. This right here, this is our Z series. Okay, so when we look at those, we are going to have our Z series and our capacitor is going to be equal to, so if we add these guys up, so Z total, our capacitor is going to be 0 minus J 2286. That's going to be added to the 1200 ohms. And then when we take these guys, we do this parallel branch. These two guys, so our Z parallel total is the 1.3K in parallel with the 5.1K. That's going to give us 1036, and there's no capacitance, so it's all real. So then this is going to be added to the 1036 next to it. And then remember, plus J of 0, plus J of 0, because it's just pure resistance, no reactive components. So the Z total comes out to be 2236 minus J of 2286. We plug that in. We're going to convert this guy into polar because we're going to be dividing it. So our Z total comes out to be 3,198 ohms at an angle of negative 45.633 degrees. Now we have the total impedance of the circuit. Now we can calculate the current, which then we'll use to solve for the voltage of our parallel system. So the current total we have is 5 volts peak to peak, at 0. We divide by this total resistance of the circuit, 45.633 degrees, and our current comes out to be 1.563 milliamps in peak to peak at 45.633 degrees. So like I said, so the reason we want to do this, we combine this whole thing together so we pretty much have this circuit. So this is our Z series, this is our Z parallel total, and we want to find the voltage drop across here. So we're just simplifying it down as far as we can, as far as we need to get it into where we can solve for what our AC voltage is going to be. Okay, so now that we have this current flowing through those two series resistors, the groups of resistors that we've combined together, we find the voltage out is equal to the voltage drop of the parallel total. So we take the 1.563 milliamps peak to peak at an angle of 45.633 degrees. We multiply that by the parallel resistance that we have. So up here is our Z parallel. So we have I total times Z parallel total, which is 1036 at an angle of 0. So the voltage drop we have is equal to 1.619 volts peak to peak at an angle of 45 degrees. Which, if you remember, at our lower critical frequency, we should be at positive 45 degrees. With a little bit of error, but generally we're going to be right around plus or minus, I'd say 5 or 10 degrees. We're going to be right there at 45 degrees. So now this gives us the voltage out peak to peak. So remember that when we're combining AC and DC signals together, our peak to our voltages is going to be looking like this. So this is going to be our V out peak to peak, and then it's going to be riding on our V out DC. So now we can calculate what this maximum value is and what this minimum value is. And so we want to take half of our peak to peak value, because remember, peak to peak goes from the top of the positive cycle to the bottom of the negative cycle, and we only want to look at how far up above the center line does it go. So with that, we can find our V out max by taking our VDC and adding half, or our peak value, in voltage. So voltage peak to peak divided by 2, this value is going to give us sorry, it looks like a smiley face. This value is going to turn into 0.81 volts peak. So then our V out max is equal to our 3.25 volts plus the 0.81 volts peak. And that's going to give us the maximum voltage that this is going to swing to, which is 4.06 volts. And the angle is still going to carry because the AC is, like I said, is just riding on top of that DC signal. The V out minimum is equal to the VDC plus our V out peak. So we have the 3.25 volts minus the 0.81 volts, and that's going to give us 2.44 volts. So what we're going to see is on our output is it's going to go down to 2.44 volts and come back up to 4.06 volts. And then the difference between those two is we take that value divided in half, the difference between those two, and that's going to give us our DC value. So that way we can still calculate based on what the measurements that we're getting. So there's the first part of the problem. We went through and we found what is our voltages out and what is the range in the voltage. What's it going to be changing due to the AC signal at our first critical frequency. And again, we can verify and know that our math is good because right here, when we're looking at our total impedance and our total current, the values of our angles are right at positive 45 degrees at our first critical frequency at the lower end. So now that we have this, we're going to move to the next step. Now we want to solve for our critical frequency 2. So now the first step is we need to find our R Thevenin across the capacitor 2. So the first thing that we have is we're going to short the power supplies. So we're going to short our generator, short our VDC, and we end up with, let me draw this in the same orientation. So this is our VGen right here that's been shorted to ground. We have this value here, which is our capacitor 1, but remember at a high frequency, this is going to be a short, so we're not even going to take it into account. We have R1, we have R3, we have R2, and then this is where our capacitor 2 lived, and this is where we want to take our R Thevenin at capacitor 2. So R Thevenin at capacitor 2 is going to be equal to R1 in parallel with R2 in parallel with R3. So that value is going to come out to be 566.473 ohms. Then, when it's all said and done, we can find our critical frequency the same way we found the other one. 1 over 2 pi times the 566.473, multiplying that by the capacitance which we had, which was 470 picofarads. That comes up with a frequency of 597.782 kilohertz. So now we have this frequency, so we're going to go through and do the exact same thing that we just did up here for our critical frequency 1, but we're going to solve it based on this frequency, our critical frequency 2. Go away. So first things first, we're going to, we can kind of come back here and we're going to reference this picture because this is not going to change other than we're going to have capacitor 2 is going to be there versus capacitor 3 or capacitor 1. So when we redraw our circuit, we have our RGen and the VGen. We have capacitor 1, but capacitor 1 at this high frequency is going to be a short. We have R1, branches off into R3, R2. We have our capacitor 2. And then all those guys are going to ground, and our V out is right here. So we got R2, R3, R1, Rgen, Vgen. So again, R1 is 1.2K, R3 is R2 is the 5.1K, and R3 is the 1.3K ohm resistor. This is 50, this is 5 volts peak, and our frequency that we're using is right here. We have 470 picofarads, and we have 1.817. Nope, that was a different problem. 77.08 microfarads. So again, just to kind of prove that these values are equal, when we go through and solve for these guys, so our x of C1 and our x of C2, to show that C2 is essentially a short, we know that x of C2 is going to be equal to this R Thevenin value up here. So it's 566.473 ohms because we just solved for it. And then our x of C1, if we plug this into the equation, so we have 2 pi times 597782. We multiply that by the 77.08 micro, so the frequency times our capacitance times 2 pi, take the reciprocal of that. This value is going to be 0.003 ohms, which is essentially the resistance of a piece of wire. So we're not even going to worry about that because it's so small. So now we have that. We're going to find our Z parallel total. So again, this group right here is our Z parallel total. This group right here in yellow is our Z series. So our Z parallel total is going to be R3 in parallel with R2 in parallel with capacitor 2, or at least our X of C2. So since these two guys are resistors, R2 and 3, I'm just going to go ahead and combine those together. So that's 1036 at 0 in parallel with the 566.473 at negative 90. So we're going to do product over the sum on these guys because there's only 2 branches, and since we've already combined the resistors together in one, we can do that. So we have the 1036 at 0 multiplied by the 566.473 times negative 90. And then we're going to divide that by the 1036 minus j of 566.473, just adding them together. This guy needs to convert into polar so we can do the division. And that comes out to be 1181 at negative 28.669. So then we multiply the 1036 times the 566 and change, divided that by the 1181. So the impedance total for our parallel section we get comes out to be 496.923 ohms at an angle of negative 61.331. Remember, we take the 0 plus the negative 90 because they're multiplying, and then we subtract the negative 28.669 in there, and that gives us a net of negative 61.331. So now that we have that, we can go through and we can solve for the next part. So our Z series is going to be equal to, or our Z total because now we have everything reduced to a single. We have our gen, R1, and our R parallel total, essentially is what we got here. Or our Z parallel total, I guess I should call it. Okay, so our Z total is going to be equal to the 50 plus the 1200 plus this value we need to convert into rectangular so we can actually add them together. So that comes out to be 238.398 minus J of 436.003. So we convert our parallel total into rectangular so we can add them together. So we have the 238.398 minus J of 436.003. We combine all these guys together. The impedance comes out to be 1488 minus J of 436.003. We need to convert that back into polar so we can divide it. And our impedance total of the circuit comes out to be 1551 at a negative 16.331 degrees. Well, then you might be thinking, well, our impedance isn't going to match up, so we must be wrong because at our critical frequencies, we should be getting close to 45 degrees. And you're right, we should be. But you also have to remember that we're not quite done yet. We only have the impedance. So now we need to solve for our current, and then we're going to multiply it across our impedance of the parallel branch. So remember, this guy right here is what we're going to be multiplying against. So if we have 61 degrees and 16 degrees, we combine those together, and in such a way where our current's going to flip polarity because we're dividing 0 by this value, so it's going to go from a negative to a positive. So we're going to add, and you can be like, oh, hey, look, we're getting right there. The numbers are starting to match up. So, don't be quite alarmed if like your impedance or your current don't exactly equal 45 degrees. You have to remember, it's still taken into account the voltage drops being taken, or the voltage of the parallel portion of the circuit, which also has a phase angle, where before we had nothing because we had an open, so the capacitor wasn't involved in it. But now that the capacitor is, it's changed your phase angle a little bit, and so now we just have to remember, kind of look ahead at the angles. What's going to be multiplied by what? Do these values start, are they starting to add up to the 45 degrees? Things like that. So now that we have our impedance, we're going to continue on. We're going to solve for the current. So the current is going to be our 5 volts in peak to peak, and that's at a 0, divided by the 1551 at a negative 16.331. That's going to give us 3.224 milliamps at an angle of 16.331 degrees. So right there's where I was telling you that it flipped from negative to positive. So when we're going to combine these guys with, we're going to multiply our current times this value, that's when we should see the 45 degrees appear. So the V out, like I said, is the current total times the impedance of our parallel branch. So we have the 3.224 milliamps at an angle of positive 16.331 degrees. That's going to be multiplied by the impedance we found, which was 496.923 at an angle of negative 61.331 degrees. So again, we multiply the constants together, add the angles together. So the V out we get is equal to 1.602 volts peak to peak at an angle of negative 45 degrees. And there's where we should see it. So now that we have that value, now we need to solve for our max and our min at this range. So remember, our V out max is equal to the voltage DC plus our voltage out in peak. Our V out minimum is equal to the volts DC minus our V out in peak. So we have to take this 1.602 and divide it by 2. So that's going to give us a 0.801 volts. So it's our DC plus and minus this 801 millivolts. So the V out max is equal to 3.25 plus 0.801 volts. And V out minimum is equal to are 3.25 volts minus the 0.801 volts. So V out max comes out to be 4.051 volts, and V out minimum is equal to 2.449 volts. And these should be fairly similar to what the critical frequency 1 was. So if we come back up and look, we had 4.06 for our max and 2.44. We come back down and look, we have 4.05 and we have 2.44. So we're still right in with a few hundred or a few tenths of a volt difference between those, and that's right where we should be. And this is due to rounding, due to some some of the assumptions we're making. They're not going to be exact, but they're going to be right there with each other's what they should be. Okay, so now the last step that we have, and there's one more to do, and that will be the end of this video. We need to find our middle frequency. So at what point is the voltage going to be the highest on our output? Then we can base everything in dBs off of that once we know the max output we can get. So to do that, we call this our F middle. We solve that by taking our critical frequency 1, multiplying by our critical frequency 2, and taking the square root of that. So F middle is equal to 903.238 times 597,782. We take the square root of that sucker, and that gives us a middle of 23,237 kilohertz. So this gives us our last, critical frequency to, I use that term loosely, but this gives us our last frequency to use to solve for this. So we're going to do the exact same thing that we've been doing based on all these guys. So now the assumptions we have, we're right smack dab in the middle of where this guy is operating. So neither C1 is going to be a short, nor C2 is going to be an open right off the bat. We have to kind of figure out and determine what's going on. So again, we're going to redraw here our AC circuit. So we got C2, we got R2, R3, R1, Rgen, Vgen, and there. So we got 1.2 kilo ohms. We've got 5.1 kilo ohms. We've got 1.3 kilo ohms. We've got 4070 picofarads. And I forgot, this capacitor has to be in there too. And that's 77.08 nanofarads. That's 50 ohms. Okay, so now we're going to look our X of C1. So we, the same thing, we use our frequency times our capacitance times 2 pi, take the reciprocal of that for both of these guys. We end up with an 88.858 ohms. X of C2 is equal to 14.573 K. So now when we go through and solve this guy, we're going to go through and solve this guy just like we would normally. So now we're going to look, and this right here, this is going to be our parallel total. So this is going to reduce down to one single value. So our Z parallel total is equal to R3 parallel with R2 parallel with our X of C2. So again, I'm just going to combine these resistors together because they're quick and easy to do. So this is 1036, and since we've already found that value several times, I already know that's what it's going to be. I can save myself some of the hassle. So we've got 1036 at 0, and that is in parallel with the 14573 at negative 90. So again, we have two branches, so I'm going to use the product over the sum to save myself a little bit of work. So I have the 1036 at 0 multiplied by the 14573 at negative 90. and then those are going to be added together. So we have the 1036, remember this is 1036 plus j of 0. This is 0 minus j of 14,573. We can combine those together real quick, 14,573. And then we're going to take this, convert this guy into polar, and that value is 14,577, right? Let me double check that. I don't know if I think I might have made a mistake there. Let's see, so we're going to have converting from rectangular to polar, so 1036, and then 14,573. What did I do wrong? Anyway, okay, so I'll just continue on. Sorry about that. I just realized I kind of screwed up a little bit of my notes. So with that, I had this wrong value here. So the rest of my values are going to be off. So when we convert the 1036 minus j of 14,573, that turns it into 14,610 at an angle of negative 85.934 degrees. Okay. So then we're going to multiply the 1036 by the 14,573. So these two guys are going to pretty much cancel each other out. There's going to be just a little bit left. So this value is going to be slightly less than what we started with because it's in parallel. That's what we should see. And this guy, you know, we kind of look, this is a little bit 10 times larger, so we should be right close to the 1036. So let me do that real quick on my calculator. So we take 1036, multiply that by the 14,573. And then we divide that by the 14,610. And so that gives us a total of 1033 at an angle of, so we take negative 90 minus a negative 85.934. So we're going to add 85. We end up with a negative 4.066. So yeah, on mine, it was carried too far, one decimal place out too far. So, all right. So now this is our Z parallel total in polar form. We need to convert this guy into rectangular because we're going to add him to the impedance of the generator, the capacitor, the X of C1, and our resistor 1. So we take this guy and we convert him to polar. So we take the 1033 and the negative 4.066, and that gives us 1030 minus J of 73.245. Okay. Now that we have this value, remember, this is just our parallel value for all the components, its impedance in rectangular form. We're going to find our Z total. So we have our 50 ohms, we have our 1200 ohms. So this is our gen, R1, and then we have our 88, and I'm going to minus J of 88.858. Then we're going to add the 1030 minus J 73,245. We combine all that together. So combine all of our real numbers and all the imaginary values, and our Z total comes out to be, so 50 plus 1200 plus 1030 is 2280. And then we have an 88 for our J's, 858. We're going to add that to a 73,245. And that gives us a combined total of minus J 162,103. So now we're going to take this value, convert it back into polar because we're going to be dividing it. We have 2280 and a negative 162.103. So that gives us a grand total of 2,286 ohms at an angle of negative 4.067. So we have this value coming up again, the 2286. We've seen it a couple of times. Now we're going to solve for the current total of this entire circuit. So 5 volts peak to peak at 0 degrees divided by the 2286 at negative 4.067. We divide that out. We get 2.187. And so I'm just looking back at my notes at what I had. And so at that mistake where I made up here, I'd added one extra digit to this, so it was 140,000. But either way, when it comes through all of this math, my current total from what I had done when I made my error was 2.185 milliamps. So even though I had increased that resistor, made it a lot larger, I didn't even affect my outcome because it's in parallel and it's going to just drive that lower value. So luckily I made that mistake at that point instead of somewhere else where it really would have thrown my numbers off. But either way, so we end up with, doing it the correct way, we end up with 2.187 milliamps peak to peak at an angle of 4.067 degrees. Now we need to go through and find the voltage out. So we're going to take our current total and we're going to multiply that by the parallel total. So we have 2.187 milliamps in peak to peak at an angle of 4.067 degrees. We're going to multiply that by our parallel total, which we found up here. So we have 1033 at an angle of negative 4.066 degrees. This comes out to be 2.187 milli, that's micro, milli, times 1033, and we get 2.259 volts peak to peak at an angle of 0.001. So essentially 0 degrees. We're at, a thousandth of a degree. That's not going to matter for what we're doing. Now the last part we need to do is solve for our V out max and our V out minimum. And so we're going to take our voltage DC plus our voltage out in peak. Minimum is going to be VDC minus the voltage out peak. And so when we do that, we get our 3.25 plus, we take this voltage and we cut it in half. So we take the 2.259 divided by 2. So this is going to be 1.13 volts. This is 3.525 minus 1.13 volts. So the V out max is going to be 4.38 volts, and the minimum is going to be 2.12 volts. So there's our max, there's our minimum. So you're also going to see here at this point, we're going to see a lot more of our AC signal out than we did at either of the two critical frequencies. So here we've got 2.2 volts, 2.3 volts peak to peak coming out of our output. On our critical frequencies 1 and 2, we had 0.8 and 0.8. So at our middle frequency, that's when we're going to see our largest AC signal coming out, which is going to be important when we start getting into the transistors, because that's going to affect, the max and mins of our amplification. How far up can we go? Are we just going to start clipping it off at certain points? We're going to, shove it into a different position, try and pump more voltage through it, but we can't. Things like that. But the whole idea is now we're able to find out where is my AC signal going to be sitting? What's the maximum? What's my minimum voltages? What's that DC threshold, which is the difference between the two? Where, all these different values. Now we can go through, we can solve for power, we can solve for, what size components we're going to need. And when we get into the power supplies, that's going to be important because we're going to be filtering out this AC signal to where we have, a very, very small AC portion coming on our output, but we have a huge value sitting on another resistor inside. And that resistor has to have a lot of heat dissipation, otherwise it's going to burn up. And that's why you guys are going to see, like, if you were to crack open one of your power supplies, like for a phone or a charger or for a laptop or something like that, inside you would see a big transformer, and then you'd see several diodes, then you'd see a bunch of capacitors to filter it out, and then you're going to see a little resistor, and then you're going to see a great big huge resistor. That huge resistor, is going to get hot because it's going to be taking a lot of the AC that we don't want. And also splitting up some of the DC, so it's going to have a lot of power going through that resistor compared to what we have going out. But either way, like I said, so this is how we're going to go through. And then also, if you notice, our angle is 0 degrees. So at our midpoint frequency, or really anywhere between our FC1, FC2, it should be getting close to 0 degrees. So we're going to start at 45 degrees on FC1, and that angle is going to get less and less and less until it hits 0. And then at this point at our F mid, that's going to be the highest point where we're going to be at 0. We're going to have the most voltage out, and then the voltage is going to taper off again a little bit till it gets down to our critical frequency value, and our angle is going to shift back up, or continue to shift down to the negative 45 degrees. So again, those are the patterns that we should see. We should see a plus and minus 45 degrees at the critical frequencies. At our middle, we should see a 0 degree phase shift, right at the dead center between those 2 points. So anyway, that is frequency responsive AC/DC circuits. So there's not a lot of new material. In fact, the only new thing was just the assumptions that we had to play with a little bit more at high frequencies, what's open, at low frequencies, what's shorted, vice versa, all those different things. Other than that, all it is just applying everything that we've known and we've learned so far and combining it all together. So like, just, so you guys don't get overwhelmed, like you guys know how to do this stuff. We started out with resistors. You learned how to put those in series, learned how to put those in parallel. Then we did combinations of those. Then we introduced capacitors and what the DC does to those guys. And then we moved into the AC section and we learned what does the components do under AC conditions. Then we learned about, okay, now that we've seen what the components do, and we also introduced inductors, what do these components do? How can I utilize them? Then we started building filters. Now that we have this filtering capability where we can start modifying our output based on the frequency, now we've combined them into another system where we're literally a system with the AC and DC portions, to where now we have both parts coming into the same circuit and giving us, a value that now we can control and we can manipulate. So we increase this VDC, we decrease these ratios, things like that. We can shift this V out wherever we want. And so the next part that we're going to learn about is we have one more video, and it's going to be a real quick one. It's just kind of more of a review of diodes. But what we're going to do is we're preparing you guys to be able to make and build your own power supplies. So we're going to be talking about clippers, rectifiers, that kind of stuff in my next video this week. And like I said, they're really, really easy. It's literally what is a diode doing to an AC signal, which we did talk about earlier. I kind of gave you guys the spiel about it beforehand. And so it's just a quick matter of review real fast. And then next week, we're going to get into power supplies. Now, these are fun. They're difficult, but they're fun. Okay. So the thing here is now we're going to be taking 120 volts coming in from the wall. Like, you're going to plug those big transformers I gave you guys into the wall. You're going to have a voltage coming out. It's going to be about 46 volts, give or take. And then what we're going to do, and we're going to have a 46 volt peak AC signal. We're going to run it through a series of circuits and some diodes, some capacitors, and things like that. And then when we're finally going to be done, we are going to have it spit out a specific voltage. So just like if you look at your power supplies for your cell phones, computers, whatever, you can see they have a rating on them for an output of DC volts of some value at some current. Well, the input value is 120 volts AC. And so we are going to be building those blocks to convert AC signals into a DC voltage. I had one of my students last semester, his brick died for his computer, and he didn't have a replacement. It was on order and it was coming. And so what he actually did is he built his own power supply temporarily to power his laptop while the replacement came in. Now, I don't necessarily suggest doing this. He was okay with it, and I warned him about it because it was an older laptop, but he had some stuff on there that he was using, some spreadsheets and whatnot. I told him, with that, it's not regulated. Like if there's a spike or something, that power supply could take out your computer because there's no protection circuits in it. Because that's what you guys are going to be learning more about in second and third semester is how do I provide protection for my circuit? Because again, if you go in there, you short out the power supplies that we're going to build this semester, something's going to burn up. It's going to happen. So that's one thing we have to be careful for. But then when you get into the later semesters, you're going to learn, hey, I can put in a current limiting circuit. I can put in this. So if the current exceeds so much, this device turns on, takes the heat, can withstand it, and then we shut the whole thing down and then, restart it and make sure we do it. But that's one of the tests in third semester is you're going to build a power supply that you get to take home, which is something to look forward to. You're going to turn it on, full voltage, full current. We're going to short the supply and we're going to leave it for an hour and see what happens. If it burns up, you got to rebuild it and there's something wrong. If it doesn't, you pass that portion of the lab. Like that's one of the final projects in third semester. So anyway, this is the frequency response. This is how everything works. This is kind of a little preview of what's coming. And again, don't give up. Keep working hard. Do what you guys need to. If you need somebody to talk to just to see another human, please let me know. I've got the Zoom calls going. You can call me. You can text me. Whatever it needs to be. And again, hopefully you guys are doing okay and you guys are staying safe. And like I said, let me know if there's something that I can help you with, or if nothing else, you just need somebody to talk to. I'm here for that as well. So anyway, hopefully you guys at least enjoyed the video somewhat. It was a little bit educational. Well, hopefully a lot of it educational, a little bit fun. But with that, enjoy. And as always, if you have questions, please contact me. We'll talk to you guys later.